So hello and good morning. I'm Ganesh. I'm an assistant professor at the Indian Institute of Technology, Bombay. I'm with the Department of Computer Science and Engineering. So I had earlier planned to present a tutorial on scalable entity annotation in search, but looks like you already had a tutorial on entity annotation linking. So I've decided to present some perhaps what in my opinion are deeper questions and some interesting research challenges in the area of entity annotation. I'll be focusing primarily on vertical search. One aspect of vertical search being enterprise search. So enterprise search could be enterprise data could be data from a company like Yahoo. The internal data could be university data, and more broadly I'm also interested in academic search, more broader than what Google Scholar has to offer, including search on code basis, search on courses, etc. So when I use the word enterprise scale, I really mean a bunch of organizations, a bunch of sources of the data which are known well in advance. So there are two components to my talk, and they are going to be fairly interleaved. One is information extraction and entity disambiguation and resolution, and the second is searching over entities and relationships. But as I said earlier, they're going to be fairly interleaved for one reason, that I would like to scale up these operations, and I find that at some level an artificial divide between processes for information extraction and processes for search, that artificial divide needs to be at some point of time gotten rid of. So I'll elaborate on what I mean. So let me present some motivation. So let's say we are interested in finding professors who were keynote speakers at a particular conference. Or here's another question, people from computer science and electrical engineering departments who have collaborated on a project. This could be university specific, this could be area specific, country specific. So how do you detect professors? How do you understand what a conference is? And how do you understand what a keynote speaker is? And how do you find instances of these in a collection of documents? The second question is about finding people from computer science. So it need not be professors, it could be research scholars, it could be undergrad students. So and there's a concept of a project. So again, you need to find instances of these types. Of course, another underlying problem is how do you identify that project, how do you identify that project should have been a type or people is a type. So that's something we will not address in this talk. We could assume that if at all there are queries of this sort, they have been typified in some sense. By the way, please feel free to interrupt me during the course of the discussion. So here's another example. So let's say you wanted to find information on Amit Singhal. Now, there's no more, there are no qualifiers for Amit Singhal, but you really like to explore concepts related to Amit Singhal, activities. So the whole idea is you want to deal with things and not strings. And there's this Google block on the Google knowledge graph. And of course, I was speaking to Peter on the way, and he talked about the Yahoo knowledge graph, which I'm not very aware of. But I'm sure these are very interesting problems for almost any search engine company. So these complex queries could be entity queries, could be entity relationship queries. So I distinguish between these two. For example, finding experts on databases who are related to Microsoft. So you're not really looking for a type beyond just experts. But in the second class, you're looking for a relationship between two entity types. In this case, IIT Bombay alumni and companies related to search. So what does it take to go from keyword-based search to semantic search? So our experience shows that if we just pose these structured queries, the structure being in the mind of the searcher, if we map these to keyword queries, typically top 10 results will not contain relevant documents. And it's also difficult to formulate these queries just using keywords. You need to empower the searcher with a syntax more than just keywords. So we're going to assume that there'll be a query language. In fact, we'll bring in the query language a little later. And the answer to these queries often require extraction of entities and their relationship from different web pages. Oh, what did I do? So what are the differences between enterprise search, or rather intranet search, or kind of vertical search versus search on the internet? So we just highlighted some differences. I'm going to use intranet enterprise a bit interchangeably. I'm sure some of you find it an abuse of notation, but I guess and I hope you understand what I mean. So intranet documents or enterprise documents, they are created for simple dissemination of information rather than to attract and hold the attention of any specific group of users. And the second difference is that a large fraction of queries will have very few correct answers. So if I want to find out database researchers in the Bay Area, so I'm looking only for database researchers, and by Bay Area I need to really look at the geography of the region. So the fact that very few answers should be retrieved is something that web search engines might not be able to factor in, because they need to cater to a large spectrum of queries. And some of the content in intranet might not be search engine friendly as well. So for example, while you would expect search engine companies to typically use algorithms like PageRank and bank on popularity, some of these information heavy web pages might not have hyperlinks that would favor them in terms of the PageRank algorithm. So while these differences exist, enterprise search and IE might benefit from information on the internet, as will be discussed later. So yes, there is possibility of harmonizing web search and enterprise search, but for the first part of the talk, we will not look at things like popularity. We're interested in precise results. So what are the building blocks for an enterprise search system? This is a family of search systems over several conferences that we are trying to distill into this part of the presentation. So they typically look at a family of entities, their types and interrelationships. You need an annotated corpus with reference to those entities. You need a query language that supports formulation of knowledge seeking queries. And you need efficient indexing so that you could retrieve results quickly. Ranking functions that go beyond link structure of documents. This again we will not talk about, we will not refer to in this presentation, but there is a lot of work on ranking for entity and relationship retrieval. So this is a typical architecture. You have input query and there's some query processing. Now this query processing is going to basically look at the index, and what sits in the index is processed collection. So the process collection has annotations with reference to some knowledge base. This knowledge base could be as large as Wikipedia, could be some very small ontology. So by ontology I refer to a large category of knowledge bases, or including internet encyclopedias like Wikipedia. Now the real hard work is here. But there's some hard work here, but the real challenges, in my opinion, sit here, which is how do you process this corpus, how do you scale up entity annotation processes. Some of these annotation processes require a lot of natural language processing. How do you scale them up? So we will spend some time on this aspect. And as I said, ontology could be replaced by some larger internet encyclopedia like Wikipedia. So this is just a placeholder. So we look at entity annotation in two parts. One is information extraction, which generally refers to annotation with respect to a small type system, and entity disambiguation, which to me is dealing with type systems of the order of millions of types. And then the third part, we'll talk about leveraging structure between entities and finding documents, searching for documents which help you get hold of those entities. So let's look at information extraction for simple type systems. So this is a very typical definition of information extraction. Given a schema consisting of entities E1 to En, you need to find all instances of the schema from an unstructured source S. So in this example, you're looking for instances of company names, designation, person names, date and time, and this is some news article. So the color coding should say it all. So Microsoft Corporation is a company name, a CEO is a designation, there was a mistake in the color coding there. Bill Gates is a person name. So information extraction is typically about finding these instances and populating a database. So Maya spoke at length about these RDF kind of triplets. It need not be triplets, it could be, in general it could, the arity of these relationships could be 5 or 6. So historically this problem has been tackled by message understanding conference. In fact, this entire definition comes from there. So there was a competition style conference organized by DARPA which led to the release and evolution of several information extraction systems. There are several of them mentioned here, very old ones from Circus, Fastest, Lassie, etc. And most of them were rule based. Some of them were built on machine learning models. So broadly there have been two kinds of approaches for information extraction and named entity recognition. One category of systems is based on learning, so using statistics of features, of word counts, etc., and looking at those signals to decipher what would be a named entity in a piece of text. And this typically requires a large amount of training data, because several of the features that these models employ are lexical in nature, which is word specific. So the annotators are cheap. The annotators are cheap in the sense that the final set of annotators are often very easy to deploy. The learning process becomes easy, but obviously what you need to invest on heavily is a training corpus. The other approach is knowledge engineering, rule based, developed by experienced language engineers, make use of human intuition. And there are also several learning systems which learn rules. So learning systems could learn probabilistic models, could also learn rules, but knowledge engineering, the focus is primarily on incorporating the expertise of the experienced language engineers. Now the interesting part is whether you realize it or not, for learning systems you have to do some knowledge engineering. How do you define the features that would provide good signal for entity annotation? So in fact most learning systems can benefit from knowledge engineering systems. So the divide is not as apparent as it's not so stark. Rules can serve as features, and in fact there's a lot of recent research on doing rule mining with the help of language engineers to improve the performance of learning systems. So what do these machine learning systems do? So they break the entity annotation task into two parts: recognizing entity boundaries. So imagine a sentence here: Argentina played with Del Bosque. So you need to identify the boundary for Del Bosque, which is probably a club name. So, it's a person name, sorry, it's a person name. So identifying these boundaries is one task, and then classifying the entities in the respective categories. So there's a lot of work on that is focused on one or the other of the tasks. Some work on doing the two together. And there are different formats for identifying token boundaries and identifying the label set to assign. So there is this IOB, which is begin, inside, outside, which basically means that if del gets tagged as B per, this means that del marks the beginning of a person instance. Argentina is the beginning of a location, but there is no intermediate word for location, so location ends here, whereas del boss actually continues into the second token. So there's begin, inside. You often also have outside, O standing for outside, to help you mark the end of the annotation. Now, there'll be a lot of studies on using only begin and end annotations as against begin, inside, outside annotations. So the results have been mixed. So identity finder was one of the earliest named entity annotation systems which made use of machine learning, and that was based on hidden Markov models. There are versions of identity finder today, I guess, with conditional random fields instead of the hidden Markov model. And the basic idea of these models is to capture transition between these labels. So the fact that a person has begun might provide trigger for an hyper to be labeled, to be the label for the next token. Of course, it's not just the presence, the previous tag, but also the features, the surrounding contextual features that matter. So models like conditional random field and hidden Markov models, they help you capture with clean semantics the interplay between local contextual features in terms of the text surrounding the tokens and the labels on the previous tokens. And the features that this model employed, for example, was capitalization. So does the token start with a capital letter? Numeric symbols, punctuation marks. So for example, you might have a comma following a location name, position in the sentence. So there are certain types of named entities which you don't expect to occur at the end of a sentence. So obviously these kinds of biases are learned from the corpus. So for email corpora, you could have sentences ending with names, in fact beginning with names and ending with names, because they might just turn out to be signatures. Whereas for news articles, the story might be different. So the goal is let the corpus decide which of these features should act as triggers for which class of named entity tags. So yeah, so this was the earliest comparison of some rule-based annotation versus a machine learning-based technique. So it was found that identity finder with very cheap kind of training process, but with intensive labels collection, gave you 94.9 F measure, whereas the best rule-based method with a lot of intensive input from the language engineer yielded just a 1.5% improvement. And the results were similar for another language, Spanish. So what was the size of the training data? So as you can see, this in that period, this was a sizable data set. Of course, now we have much larger named entity data sets. One of the largest named entity data sets is the Enron collection, Enron news email dump. So we will focus more on rule-based extractors for the following two reasons. First of all, there's only so much you can do with a machine learning model if your features aren't good. And the machine learning based extractors often use rules as features. So better the features, better is the model. That has been proved repeatedly. And the second reason is coming from my own industrial experience at IBM Research for 5 years. So in many of these applications, some amount of explainability is found to be important. So if you have probabilistic models, like hidden Markov models, the explanation for a particular annotation coming up is primarily in terms of the probability values and the map distribution. You need to look at how the Viterbi algorithm really is functioning. So the explainability, for example, if you were to debug a piece of code, you would like to look at the stack trace. So the stack trace, so to speak, would be the trellis for a hidden Markov model, which is often difficult to make sense of. On the other hand, for rule-based annotators, that explainability is easier. So for these two reasons, I'll focus on rule-based extractors for, I would say, for the next half an hour. So what's the anatomy of a rule-based information extractor? So I can tell you that these rules can be fairly complex. And one recently released rule-based extractor called SystemT from IBM Research has built on top of the SQL language and added a lot of relational constructs and also span constructs to make sense of the interplay between the surrounding contextual features and lexical resources such as dictionaries and WordNet, etc., in order to be able to unambiguously annotate text. So what is the anatomy of rule-based information extractor? This is really, again, at a high level. You can get into more details if you're interested. So the first set of inputs that these extractors look for are basic features. These are features like, capitalization, regular expression matches, very simple regular expression matches on the tokens. So for example, we met Miss Anna Smith from Melinda Gates Foundation. So Anna is capitalized. Anna could belong to some first name dictionary. Smith could belong to some last name dictionary. These dictionaries could also be obtained from the training data. The second phase is candidate definition. Now, candidate definition is really about putting together some of the clues from the basic features into identifying candidates for potential candidates or potential named entities. So here we have these rules have helped you identify that Miss Anna Smith is a person candidate with salutation, and Anna Smith is a person candidate. There's no salutation. So as you can see, these candidates could overlap. There could be noise. So Melinda Gates has been found to be a person candidate, but obviously is not a person. So the belief is that you really can't solve the entire problem in one shot. You need to identify candidates and then need to introduce some refinement. So what would the refinement tell you? Well, Melinda Gates Foundation was an organization and Melinda Gates was a person. If a person is a substring of an organization, you get rid of the person name. And the final phase is consolidation. So putting together, for example, you could have overlapping matches of persons. Person candidate with salutation was Miss Anna Smith, and Anna Smith person candidate was a substring. Well, you need to decide whether to retain the longer one or the shorter one. This is just one example of consolidation. And I could draw analogy from database from SQL queries for each of these phases. So you could think of candidate definitions to be like join queries, but join with some additional contextual qualifiers. So here's a bunch of existing technology options for rule or grammar-based annotation. So CPSL is a common pattern specification language. It forms the foundation of a package called GATE, General Architecture for Text Engineering, from Sheffield University. There are other implementations also. And the dominant paradigm in in these rule-based methods, which basically help you discover features, discover candidate entities, is to take the document collection, process one document at a time, subject it to the basic features, the candidate definitions, the candidate refinements, the consolidation, and basically create an annotated document, and this goes into a collection which is indexed. So let's look at some example rule for identifying organizations. So let's say you have BP Marsh PLC, the USB Holding Co., the USB Holding Group, etc. So what would you do? This is how a JAPE rule would look like. So you would have a pre-context and a post-context. This is post-context. So you're looking for some match between this match demarcated by this internal tag, and you're looking for a match for let's say the USB Holding Co. So the will match regular expression the, u.s.b would match some regular expression which is defined. It's a macro defined elsewhere. In this case, this macro is called initial word. So it's a regular expression that looks for a character in caps followed by a dot followed by another character in caps and so on. You could also have caps word next, and then you could have some things optional. So you often have organization names which have comma in the middle. So in this case, the USB Holding Co. did have a comma, but in this case, this comma was optional. And finally, you have this rule required a match with a dictionary. In this case, is a dictionary called Organization Clue Dictionary, and it also matched a capitalized word regular expression. So it's basically, as you can see, the sequence of some primitives or intersections of primitives being dictionaries, regular expression, also direct token matches. And in this case, there was no context specified, but you could also have a context. So there's a problem with these existing approaches, which we will we discussed some solutions that have been proposed in literature. And what are the problems? One thing that happens is this repeated computation for multiple occurrences of the same token. So for example, dictionary lookup. So every instance of co in the corpus will need a lookup. And every sequence of a capitalized word followed by a capitalized word needs to be computed. So this may not be required since we are looking at regular expression pattern matches, but at a higher level, not at the character level, but at the token level. Is it possible to cache some of this? There are also large overheads when you re-annotate a corpus after changing dictionary entries. So let's say you have a person sitting with the rule base. He makes some small changes and he wants to make sure that the changes reflected are as he desires. Unfortunately, he'll have to run subject the entire collection to the rule base and then make an observation, either in terms of summary numbers like precision recall or in terms of spot checks. So here's an example. The user realizes that group is too generic what to be included as an organization clue and wants to remove its entry. Or let's say the user realizes that the at the beginning of that rule introduces too many wrong annotations and he wants to modify the rule. Now, while I keep referring to these as rules, you could think of them as features, because these could be very complex features leading to very high accuracies even in a machine learning model. So there's the optional the at the beginning removed. Or you could make incremental annotation updates by adding new rules. You might want to expand an existing rule or create a copy of the existing rule or feature, and it might be more sophisticated, but yet could make use of the processing that the previous rule was doing. So here's an example. The user wants a new rule that identifies C.B, Fairly Holding and Finance Limited. And what basically the additional entries that are required are this conjunction in the middle.